Live.
We live?
Yep.
Okay, so welcome to the first session of May 2021. It is my great pleasure to introduce our first speaker of the meeting, Dr. Jean-Remi King. So Dr. King is a CNRS researcher at the École Normale Supérieure, but who's currently working at Facebook AI Research. And his research focuses on understanding the computational basis of human cognition. So Jean-Remi completed his PhD with Stanislas Dehaene, working on the neural basis of conscious perception. He then went on to complete a Marie Curie postdoctoral fellowship at New York University, studying the neural basis of language. In his own lab, his group focuses on understanding the computational basis of human intelligence using a variety of techniques at the interface between AI and neuroscience, including the development of deep learning techniques to interpret and model neuroimaging and intracranial recording data. So it is my great pleasure to welcome Jean-Remi as our first speaker of the meeting. His talk is entitled Language, AI's Myopia, and the Human Brain. So over to you.
Great, thank you very much for this kind introduction. I'm just going to make sure that you are seeing my screen.
Yep.
Awesome, great. So thank you for this kind words, and thanks a lot for setting up this meeting. So I slightly changed the title of my talk, but I hope it won't matter too much. Before I start, I wanted to give credit to the artist behind the illustration that you see here on this first slide. His name is Noma Bar. He does a lot of these minimalistic illustrations, but I think this particular piece captures very well the issue at stake here. Namely, when we look at machine learning algorithms, which is here symbolized with a smartphone, it's easy to be tempted to see ourselves in it. And it's really the question which is at stake. Is this an illusion? Is their behavior really profoundly intelligent, or is it just a mere bag of tricks, which is empty in terms of the computations behind it? And so in this talk, what I'll try to show you is how we address this type of question in the specific case of language, using, as you'll see, neuroimaging and deep learning algorithms. Now, the overall goal that we have in mind is to, on the one hand, better understand how human processes language and how our species managed to develop this unique ability to compose and decompose symbolic sequences to share our thoughts. But it's also to try to improve machine learning algorithms in light of neuroscientific discoveries. So to tackle this issue, we are following a pretty classic method introduced by David Marr, who is a very famous computer vision scientist at MIT. And in spite of having died at age 35, he had a huge legacy, a huge impact onto the field and on how we should analyze intelligent systems. David Marr suggests to analyze the brain in particular, on cognition more generally, using 3 levels of analysis: the implementational level, the algorithmic level, and the computational level, to try to understand how the system performs each operation, each of its functions, what kind of functions it actually employs, and why does it employ these functions as opposed to something else. And these 3 levels of descriptions resonate pretty well with 3 components that are being developed in AI, namely the architecture, the state space defined by the algorithms after training, or the sequence of representation it generates to, for instance, transform images into text, or to transform paragraphs into titles, and the last component being the learning objective, the loss function. So what I'll show you is that we use these 3 types of elements to try to understand pretty much the architecture, the representation of the algorithm, and the objective of the brain in light of those being developed in AI. And for this, we use a very powerful approach, which was, I think, co-developed by multiple labs, but is perhaps best illustrated by one study from Dan Yamins and James DiCarlo. In this study, what they did is conceptually pretty simple. They recorded the neurons of macaques in the inferotemporal cortex and their response to a bunch of natural images. And they presented the very same images to deep nets trained on object categorization. And they ask a very simple questions. Are the representations of the deep nets similar to the representations of the neurons in the monkey brain? And to address this question, they try to correlate the activations of the deep nets to the activations of the brain. And because there is no one-to-one mapping, which is obvious between each neuron of the brain and each neuron of the deep net, they learn this mapping through a linear projection that we call W. Now, this is the only equation I'll show you throughout the talk, but because we're using this method again and again, I thought it could be useful to go through it. So the basic idea that you can quantify the similarity between the representations of the deep net and the representations of the brain by correlating these two sets of correlations after a linear projection. And in practice, this linear projection is simply a ridge regression. So how does it look in this particular study, for instance? Here is the spiking activity of a single cherry-picked neurons in the inferotemporal cortex in response to a variety of images, which are here sorted by categories. So the horizontal axis are all of the images, and the vertical axis is the spiking rate of this particular neuron. And you see that this neuron does not really respond to most images, but to those ones which corresponds to the block where there were faces in the image. And in red, this corresponds to the virtual neuron, to the linear projection of the deep net activations onto the brain. And you see that this these virtual neurons has pretty much the same response profile as the biological neuron. So if you were to correlate the red line and the black line, you would have a pretty high correlation value. You would say that you have a strong similarity between this virtual neuron and the biological neuron across those images. Okay. So in our work, we basically just adapt this method to the context of language processing. And we don't use electrophysiological recordings. We use functional magnetic resonance imaging here in this first study that was done by Juliette Millet when she did a internship at FAIR. The setup is pretty similar. So we present to a deep net a set of sentences that were heard by the subject. These are isolated sentences. The deep net is standard. It used to be pretty popular DeepConvNet. It's called Deep Speech 2. That was trained to do speech to text, so to do automatic subtitling. So you give an audio input and the network has to spit out some text. And we asked the question whether the activations of this kind of DeepConvNet are similar to or can linearly predict the brain responses to the same sentences. And these sentences here, these brain responses to the sentences were collected by Jan Matthias Schoffelen at the Donders Institute in 102 subjects. So when we apply this correlation analysis, we can do it voxel-wise. We can investigate the similarity between the representations of the deep nets and the representations of each and every voxel in the brain. And we end up with this kind of correlation map. It peaks here in the areas typically associated with early speech processing, meaning that you can reasonably predict the brain responses to each sentence given the activations of the deep net. And it's significant pretty much all across the cortex, which is quite remarkable. And I think here it's possible because we have these large number of subjects. Once we have this kind of correlation map, we can decompose it to try to recover or identify the hierarchy of representations in the deep net and in the brain. So in this analysis, what we do is we evaluate the extent to which each layer in the deep net specifically predicts or specifically accounts for the activation in the brain. So when we take the first layer of the deep net, we have correlation values which are only significant in the early auditory regions. And if we take deeper layers in the network, in the algorithms, we can find similarity that are significant across a much more distributed set of areas, including the superior temporal sulcus and even the prefrontal areas. So in other words, it's quite easy in practice to find a similar hierarchical organization of speech representations between the deep nets and the brain using this simple correlational approach. What was remarkable, or at least what we didn't expect, and in retrospect we should have, is that we can find the same hierarchical organization in deep convnet which are not trained. So if you take a random deep convnet that has never been trained on any kind of tasks, and you apply the very same methodology, you observe something which is similar. You find a similar hierarchical organization that I just showed you in the previous slide. Now, it's less similar to what you would have had with a network which is actually trained on a speech task, but nevertheless, you find the same qualitatively it's the same finding. So we do see that when we train a network with specific types of data, typically speech, which is similar to the language that subjects actually heard in the scanner, you find activation in a deep net which are more brain-like than if you train a deep net with speech which is coming from a very different type of language like Bengali. But nevertheless, the fact that you don't need to train the network to find most of the explainable variants suggests that you have a really strong inductive bias. So the architecture of the deep net suffices to account for a pretty large amount of the representational organization. And that's really sort of the first type of analysis that you can do. You can inspect different type of architecture and see how the inductive biases make them more or less brain-like. In the second study, I'll try to show you or focus on the algorithmic part, which is what sequence of representations does the brain and does the network go through in order to achieve a particular task. This is work that was done with Charlotte Cocheteux, who is now a PhD at in between FAIR and INRIA in Paris. And in this work, we focused on a different type of deep language model, not trained with audio to text task, but trained simply on text data. The type of algorithm that we use are referred to as transformers. And without going into too much detail, the idea is that you can take huge amount of text, huge corpora like Wikipedia or this kind of non-structured data, and you ask the algorithm to do text completion. So you either mask random words in the text and ask the algorithm to guess what those words are given the context, or you ask the algorithm to guess what the next word will be given the preceding context. And this kind of algorithm and training regime has proved to be extremely powerful. It's now the backbone of most natural language processing tasks. And you can see here an example from Hugging Face, where you can recursively generate text given a fixed and here pretty small context. Okay, so the idea in this particular study is to use these kinds of language models to again see or evaluate the extent to which the activations map onto each brain area and or are similar to each of these brain responses. For this, we used 100 fMRI subjects and 95 subjects who were reading 400 distinct sentences presented in a serial visual RSV, a rapid serial visual presentation, so one word at a time. So when we do this, the correlation analysis that I introduced you when I presented the Yamins and DiCarlo paper, this is a kind of brain map that we end up with. These are the areas which can be significantly predicted from the linear projections of the activations of a language transformer. What's nice again is that we can decompose this kind of effect per layer. And if we focus, for instance, on the first layer of the language transformer, this is a so-called word embedding layer. And its particularity is that it associates each word with a particular vector, but independently of context. And so if you have typically a word which has multiple meanings, like bank can be the river bank, or can be bank where you put your money, this will be associated with a single vector. And so it's really a lexical type of representation. It's not something which can combine words with one another in order to achieve something more than a sum of its parts, as we would say in a compositional type of representation. And finally, the last type of algorithm that we use to analyze brain data is a visual embedding. It's a convolutional neural network which was trained to recognize characters from natural images. And so you can think of this as a way to extract perceptual representations but devoid of meaning. The algorithm has no way to know what words actually mean and how they're used in context. Okay, so overall, we can do this type of analysis with fMRI. We can also do it with magnetoencephalography, and this is, we obtain a bit smoother, a bit more blurry type of effects, but overall consistent with what we observed in fMRI. But of course, the huge advantage of magnetoencephalography is that we can track the dynamic of the brain responses over time. So what you see here is the average brain response to words, average across all words and across all subjects. And you can see the classic sort of hierarchical response that starts from the early visual cortex, propagate in the ventral and dorsal stream, reach the premotor areas, and ultimately end up in the infrafrontal and temporal, supratemporal gyrus and sulcus associated with high-level language processing. Now, these are MEG source reconstruction, and even though they look pretty clean, source reconstruction can be subject to systematic types of errors. But we are doing the same type of analysis in intracranial recordings. This is data from the RAM project, where there are 176 patients, more than 27 electrodes, and this is the average brain response on within each of these electrodes to individual words. And you see a similar type of hierarchical response, which is remarkably distributed in the brain. So when we present a word onto the brain, pretty much all cortical areas get light up at some point or another. Okay, so these were the average brain responses, but of course we want to know whether the representations at the single trial levels actually corresponds to those of deep learning algorithms. And so we have these three types of algorithm which will be color-coded with three colors. We have the visual neural network trained on character recognition, which will be depicted in blue. We have the lexical embedding, which is will be depicted in green. And we will have the correspondence with a language transformer, which is a compositional type of embedding, and which will be depicted in red. So at each time sample and at each brain location, we can try to see the extent to which this particular brain response has a profile similar to the visual, to the lexical, or to the compositional type of algorithm. So at 0 milliseconds, this is a word onset. If we wait around 80 milliseconds and up to 100 and let's say 15 or 20 milliseconds, we have a peak response in the early visual areas, which is here depicted in blue because it specifically correlates with the deep convolutional neural network trained on character recognition. So we can say that these are really visual representations which are being computed here in the brain. If we wait a bit, we see that this effect propagates along the ventral and the dorsal, the dorsal and the ventral stream over here. And the color now shifts from blue to cyan. And cyan is actually a mixture of two effects of a correlation with the visual convolutional neural network and of the word embedding. So in this area, it seems that we have two types of neural code. A neural code for a visual effect and a neural code for a lexical representation. And that's great because this area is actually known to be the visual word from area. It's been described with factorial design analysis to be the area key for reading, for transcribing visual letters into meaningful words. If we wait a bit more, we see that this effect propagates along the left hemisphere. You can see that there is pretty much nothing here on average in the right hemisphere. And it's heavily green, meaning that the activity in these brain areas and at these moments of time, these responses are only accounted for, or specifically accounted for by word-to-vec or word embeddings, meaning that these are really lexical representations. Okay. If we wait a bit more, the activity is sort of going back and forth. It's quite unclear what's happening, but there are some peaks every now and then which are becoming red and which will be becoming more and more red, especially in the infratemporal, infrafrontal areas and in the temporal lobe. And ultimately, all of the brain responses that we can model seem to be color-coded here in red, meaning that these brain activations are solely accounted for by the activations of language transformers. They're not accounted for anymore by word embeddings or by the visual neural networks. They are, in a sense, compositional according to this type of analysis. So that's quite great, right? Because now we can really track in both time and space the rise of different types of representations, and therefore follow step by step the algorithm that our brain implements in order to solve, in this case, reading. Okay, but what about the computational level of organization? Why is this organized in this way? Of course, that's a very difficult question to answer. The why questions are the hardest. But what we can do is to try to see whether we can compare different types of objectives to try to see what exactly makes an algorithm more or less brain-like. And this is what we've done again with Charlotte in this paper. Specifically, what we've done is that we, instead of relying on 3 different types of algorithms and see whether they correlate with brain activity, we trained thousands of different embeddings using different types of architectures, different types of losses, different types of dimensionality. For each of those models, we compute 2 types of metrics. We evaluate, on the one hand, their ability to predict words from context. So that's the usual sort of a metric that you would use for this kind of NLP task. And we also evaluate for each of those embeddings the extent to which they linearly predict fMRI or MEG responses, in the extent to which they are similar to the brain responses to the same sentences. Each dot here represents the average effect across all of the subjects, across all of the brain location, just to collapse all of these results. And what you see overall is a pretty strong tendency. The better the model is at predicting words, the more its activations are similar to those of the brain. And that's particularly true for the middle layers of language transformers, as opposed to the, for instance, the word embedding layers. Now, because we retrain systematically many different types of models, we can quantify or identify the factors that make an algorithm more or less brain-like. And what we observe overall is that their accuracy above and beyond their training and their architecture is the factor that is the most predictive of whether an algorithm will be more or less similar to the brain. Okay, so in our opinion, this is suggestive of an element of convergence in the evolutionary sense. Language algorithms are extremely different from the brain in many ways. They are not trained with the same amount of data. They're not trained in the same way. But nevertheless, it seems that the better they are at their own task, and the more they are similar to the brain, suggesting that these 2 systems are converging towards the same computational solution. Okay, but this is really half of the story. This analysis at the implementational, algorithmic, or computational level of organization, this comparative analysis between deep nets and the brain, is only working if the 2 models, or the 2 systems, I should say, are similar with one another. And it is in many ways, right? I've shown you 2 studies, and we're doing the same type of analysis on a number of different types of language questions. For instance, we've shown that we can replicate or refound the organization of receptive field in the brain using the comparative analysis between deep language models and the brain. We can decompose brain responses in terms of syntax and semantics using this kind of approach, or identify the brain areas which are associated with narrative comprehension, again, with this type of approach. It's half of the story, because we do know that language models and deep learning algorithms in general are pretty poor when it comes to very difficult tasks. So for instance, if you give an algorithm like GPT-2, I don't know about GPT-3 now, I guess we can test it. Simple context, like there are 2 persons in a room and one of them left, there are therefore X person in the room. You can easily show that these algorithms are responding not necessarily at chance level, but with a pretty poor level of accuracy. And you would need a lot of fine-tuning and a lot of examples to be able to generalize to these kind of questions. So it suggests that these models do not understand language like we do, and therefore it suggests that they cannot be used as perfect model of the brain. At least there is something missing. And what is missing, of course, is a big challenge for both AI and neuroscience. And it would be great to try to find solutions that are inspired from the brain to try to improve deep language algorithms. One idea that we thought of, I think is pretty commonplace in system neuroscience, is to say that the human brain is not organized at all in its objective as the typical language algorithms are. Specifically, when you take algorithms like GPT-2, so these language transformers that are trying to do a next word prediction, they are focusing on a very short-term objective. They're trying to predict the next word given the context. And you have a variety of objectives, and you have also mask modeling, which predicts words from surrounding context. But generally speaking, the prediction is a relatively low-level prediction. You're here predicting words. And the idea in predictive coding, which is pretty popular in neuroscience, is that this is not how the brain is organized. According to this framework, each layer, each level of processing in the brain is trying to predict its own level of representation. So the first layer will try to make prediction about in the future about this level of representations, whereas deeper layers will try to predict deeper level of representations. Now, I'm skipping a lot of details in terms of feedback and all this, but the bottom line is that because you have this hierarchical loss, because you have this hierarchy of prediction, you would allow the deepest layer in the network to focus on the hardest problems, while the easiest problems are solved by the lowest layers. So to try to see or to test this idea that this is how brain is organized to process language, we thought of doing the same type of analysis as we've done before, but enhancing language transformers with long-range forecast representations or predictions. So in practice, what we do is that we correlate brain activity with the activations of the language transformer, and we can call this R of X. And we compare this kind of brain score, this kind of correlation values, to the correlation we would obtain if we were to take not just the activations of the language transformers at time t, but asking the network to generate predictions or to take future words and embed these predictions of these future words again into the algorithms to get an embedding of what the future should look like. And these forecast representations can be then used to try to see whether we can better predict brain activity than if you use the activations of the network on its own. And we call this F for forecast score. So it's the gain of brain prediction accuracy when we use these forecast representations as opposed to the mere activations of the deep net. So we can come up with a bunch of hypotheses. We can say perhaps there is no better forecast in the brain than in these language models. And so whether you take a short range or long range forecast in blue and in red respectively, you would have no gain whatsoever. Perhaps the brain is actually making a short range forecast as compared to the algorithm, in which case you would have a gain. The F would be peaking early on. And perhaps there is also a long range forecast, in which case the gain would lead to a much bigger or much more delayed type of curve. So we can vary systematically the distance of the forecast that we ask that we enhance the activations with. Okay, so here are the results. This is on data from 345 subjects that were collected in the Hassels lab. And each of these subjects are listening to approximately 70 minutes of spoken stories. So this is actually a lot of data, which explains perhaps why we have so clean results in this case. So again, on the horizontal axis is the forecast distance, is how far off in the future we are generating these representations in order to enhance the activations of the model at the current word. And what we see is that we have a gain when we use approximately up to 10 or 11 words in the future, meaning that we better account for brain responses to a given context if we enhance the classic language models with forecast representations of the next 10 words. If we look at this particular distance, we can observe the associated gain in brain score in the brain, which highlights the typical language system. It's heavily distributed, a bit lateralized to the left, but overall bilateral. Okay. And now finally, we can investigate what type of predictions are being generated as a function of the distance. So for instance, if we look at the short range prediction, so if we look only 3 words in the future, the gain of brain score, this so-called F value, is best achieved if we take shallow representations in the deep net. Whereas if you go a bit further off in the future, we see that now not only is it much more distributed in the brain, but the areas are color-coded in a darker color, meaning that they are better accounted for by deeper representations, by deeper forecast predictions. So this result seems to suggest that basically the brain is making a hierarchy of predictions. The early areas are making short-range and shallow-level predictions, whereas the associative cortices in the prefrontal cortex and the parietal areas are generating long-range and deep or abstract predictions. And so this seems to suggest that this confirms at least the hypothesis that we had in mind, which is popular in system neuroscience, this predictive coding hypothesis, whereby each layer or each area in the brain, each level of the hierarchy, is dedicated to predict its own future, which provides a path of difficulty to the whole system, because you can solve the easy prediction first in the first layers, such that the deepest layers can concentrate on more difficult and more distant levels of predictions. So the goal, of course, what we are quite excited about is to try to now see whether training these algorithms with this kind of hierarchical loss would improve not only the ability to map onto the brain, but also the ability to perform well on a variety of natural language processing tasks. Okay, so I hope I convinced you, not so much that we are making huge progress on this issue of brain versus AI, but that there is a valid path towards this goal by systematically comparing language processing in these algorithms and in the brain, both to try to better understand the organization of the brain in its organization at the implementational, at the architectural, at the algorithmic and at the computational level, but also in vice versa, to try to see what we can learn from the organization of the brain to hopefully improve the state of the art in machine learning. Okay, with this, before I thank you all and take questions, I'd like to thank the great team that I have the chance to work with. In particular, this work was done by Juliette Millet for the first study and Charlotte Cocheter for the next 2, in collaboration with Alexandre Grandfort. But this is part of a more general effort that we are trying to achieve, to perform at FAIR and elsewhere. With this, I'd like to thank you all for your attention.
All right. Thank you very much, Jean-Remi, for a wonderful talk.
Yes, thanks a lot. I'm sure if we were in a real room, you'd hear more applause, but this is all we've got, unfortunately, here. Okay, so I'll start with the questions. There have been a few questions posted, and I'll start with the one that was the most upvoted, which comes from Josh Vogelstein. And he says, "The data are so beautiful. I nonetheless wonder, what are the specific philosophical assumptions underlying the argument that correlations between brain activity and deep net activity can be interpreted as providing evidence that deep nets are doing profound intelligence rather than just a bag of tricks?
That's a harsh question. So I hear several criticisms. So there is the criticism about mere correlation, which I think is not completely fair, because most of the neuroscience enterprise is based on correlation, at least in terms of brain activity. It's very difficult to modulate brain responses in a causal and carefully controlled fashion. But I do understand the criticism that perhaps it's not sufficient. My response to that would be pretty down to earth. It's if it quacks like a duck and walks like a duck, it's a duck basically. So the idea is that if it can achieve the same type of task as we can, and if we show that the sequence of representation that it generates to achieve this task is similar to the sequence of representation that the brain generates, then I think this is all the evidence we need. We don't need anything else. Having said that, I don't think this is necessarily what is the main objective. I don't think the objective is to say, or is to demonstrate that AI is intelligent. I think what we ought to do is to understand the principles that guide this intelligent behavior. And I think here there is a lot to be done. For instance, here in the language algorithms, it's very clear that they can do a lot of things, but there are many different teams that are working on trying to understand or decompose the activations of the deep nets to try to understand how they actually achieve this kind of things. So for instance, how do they identify the syntactic trees? How do they compute the long-range dependencies between words? In the domain of vision, you could have asked the same type of question, like how do they recognize objects independently of their luminosity and independently of their orientations, and what are the computations that they use to try to achieve those intelligent functions. I think here we are only scratching the surface, so there are a lot of things to be done. Yes.
Yes. So there was actually quite a discussion in the question box going through some of these points. Some people said, as you did, that if it quacks like a duck, okay, that's enough. Others, however, have questioned that. Well, okay, but as you test it further and you realize, the difference, the subtle differences, maybe you realize that it's actually not at all like a duck. There was a comment from Josh Vogelstein again that if an additional set of experiments, if there's no experiments that can ever be done that will find a difference, then yes, that's true, then that's okay. But if you then start to poke it and prod it further and you see that things are different, then maybe we do still care. John Krakauer made a similar point, saying that you can be similarly sick through different causes like a virus or a bacterium, but you definitely want to know why. But I suppose you're essentially responding to that. I don't know if you want to add anything more, but
I just want to add that I don't think anyone would naively say that we have algorithms that are like humans or are like mammals already. I think we're very far from this. So this is really sort of a philosophical question, sort of a thought experiment. Everything suggests that there are clear differences between these algorithms and the brain, not only in the output, but also in terms of how they function and obviously how they learn, which is yet another issue. So I don't think anybody has this naive position. But if we were to go there, I would be happy to say that it's sufficient. I don't think we need necessarily to say it's impossible for an algorithm to be like the human brain. I think that's not a tenable position.
Okay, so before I move on to the next question, I just wanted to acknowledge that João Barbosa also asked something which is somewhat related, saying that perhaps what we get from this is not so much the fact that the correlation is so good. Actually, no, let me just read it, maybe. Let's use his words. Regarding correlations between deep nets and neural activity, isn't it expected that from a high-dimensional representation, one can decode, i.e. correlate more stuff, neural activity in this case? If so, the correlation between deep nets and neural activity is not about how similar they are to brains, but rather how high-dimensional are the deep net representations.
Yeah, so this person is certainly smarter than we are, because I didn't think of this as a big issue originally. I thought we are using cross-validation. It's not because you have a high dimension that suddenly you get everything for free. But in fact, there is structure in the input which is sufficient to account for a large amount of this correlation. So this is what I tried to show at the very beginning in the first study, where if you take a random convnet, you already achieve significant brain scores. So we do see this. We are certainly not the first one who saw that. I think there were already evidence of that in other papers, for instance, from Kell. There is a neuron paper from McDermott's team at MIT who has shown similar stuff on fMRI and music and speech stimuli. But certainly was not necessarily emphasized. And what this suggests is that indeed, there is an inductive bias. So high dimension give you potential benefits, but perhaps more importantly, the fact that it's a hierarchical network and that uses convolution also bring a lot for free, and doesn't necessarily tell you that you've learned something that intelligent. But nevertheless, what we do see is that, and this is the work from Charlotte in the second study, that the key factor that makes an algorithm more or less brain-like, at least at this stage, is its ability to predict words. And so you don't get that for free. You need an algorithm which is pretty powerful already to achieve that.
So there's additional comments from Yashua Benjo, additional questions that are all very interesting and highly upvoted. So, but we don't have time. I'm really sorry. but at least you can rest. You can be pleased. I think that you've certainly stimulated the audience. There's I guess we can probably discuss this later. I hope there'll be time. But unfortunately, I do have to move on to the next speaker, and I'm going to let Andrea take over to introduce.
All right. Thank you very much.
Thank you.